Hey guys, so it's my first time recording a lecture using screen recording software, so just bear with me. I apologize in advance if there are any kinks with this, but here we go. So we've talked about two fairness ideas in voting so far. We've talked about what's called the majority criterion, and we've talked about the monotonicity criterion, which is what we talked about in Monday's class. Now I want to talk about what's called the Condorcet criterion. So the Condorcet criterion. So first, in talking about that, when we talked about pairwise comparison, we briefly mentioned what was called a Condorcet candidate. A Condorcet candidate is somebody who wins all of their matchups. So a Condorcet candidate wins all of their matchups in pairwise comparison. Even if we're not using pairwise comparison as the voting method, we can still talk about the Condorcet candidate. A Condorcet candidate is just somebody that if we were looking at all the matchups, there's somebody who wins all their matchups. So a Condorcet candidate would win all possible points if we were using pairwise comparison. Okay, so what the Condorcet criterion says is that a voting method satisfies the Condorcet criterion if a Condorcet candidate always wins. So there may or may not always be a Condorcet candidate, but if there is one and the voting method satisfies the Condorcet criterion, that Condorcet candidate has to win. So for example, if we look at these ballots here, and we consider the matchups between each pair of people. There's three candidates here, and the matchups here is there's a matchup between A and B, there's a matchup between A and C, and there's a matchup between B and C. So what I'm going to do is I'm just going to look at one of these matchups closely, just to review how we determine the winner. So if I look at the matchup with A versus B, if I look at that matchup, what we have to do is we have to count the number of people who rank A higher and the number of people who rank B higher. So if I look at these ballots, in this first ballot, A is higher. So A is higher in this first ballot, so I'm going to circle that. A is higher. In the second ballot, again, A is higher. A is higher than B. In the third ballot, B is higher. Okay, and in the fourth ballot, A is higher, so I'm going to circle that. And in the fifth ballot, B is higher. So overall, 3 people had A higher, and then 2 people had B higher. Let me switch to a different color. So 2 people had B higher, and B was higher in that third ballot and in this fifth ballot. So 2 people had B higher. So overall that means A won. A wins this matchup. So usually we would do that. We'd figure out the number of people who prefer A and the number of people who prefer B using a preference schedule. Here we're not given a preference schedule, we're just given the ballots. But again, we can still determine the winner. So in that matchup, A wins, which is why A got 1 point from that matchup. And if we were to look at the other matchups, A wins the matchup against C, so A gets a point there, and in the matchup between B and C, C wins that matchup. So C gets 1 point. So overall, A is the Condorcet candidate because A won both of his matchups. So A ended up being the Condorcet candidate. So if this voting method satisfied the Condorcet criterion, A would have to be the winner. So again, the Condorcet criterion says that if there is a Condorcet candidate, meaning if there's somebody who won all their matchups, so if the voting method satisfied the Condorcet criterion, it means that if there is a Condorcet candidate, aka somebody who won all their matchups, they have to be the winner. Okay, so now I want to ask a question. So the first question that I want to ask is, does pairwise comparison satisfy or violate the Condorcet criterion? Okay, so let's suppose that there's a Condorcet candidate. So if there is a Condorcet candidate, so if There is a Condorcet candidate. What that means is that person won all their matchups. That person won, the person won all of their matchups. But if somebody wins all their matchups, that means they win using pairwise comparison. So this means that they win using pairwise comparison. They win using pairwise comparison. Okay, so what we've just showed is that anytime there's a Condorcet candidate, meaning anytime there's somebody who wins all their matchups, they have to win using pairwise comparison. That's what it means to satisfy the Condorcet criterion. The Condorcet criterion, to satisfy it, what has to happen is anytime there's a Condorcet candidate, they have to be the winner. So this shows that pairwise comparison satisfies the Condorcet criterion. Okay, so we've shown that this is true in all cases. Anytime there's a Condorcet candidate, meaning anytime there's a person who wins all of their matchups, they have to be the winner using pairwise comparison. So that shows that pairwise comparison satisfies the Condorcet criterion. Okay, so when you guys look back at the slides, the following slide will have that stuff that we just wrote down, showing that pairwise comparison does satisfy the Condorcet criterion. Okay, so I want to look at an example. So in this example, it's an example that we've looked at before where there's listeners who are voting on their favorite bad movie, and there's 3 choices. There's 9 Lives, which is going to be NL. There's the Emoji Movie, which is going to be EM. And there's Mulan 2, which is going to be M2. So we have this preference schedule, except we don't know the number of votes in this last column. So the first question that I want to ask is, I want to find a number of votes that we could put in that last column that would guarantee that EM, which is the Emoji Movie, would win if we use pairwise comparison. Okay. So if we want to do that, if we want to guarantee that EM wins using pairwise comparison, we need to guarantee that EM wins all of its matchups. And it turns out that to do that, we just need to make sure that EM has a majority. So we need to give EM a majority. We need to give EM a majority. So we need to give EM a majority. So why is that true? Why, if someone has a majority, will they win all their matchups? So what I'm claiming here is, if a candidate has a majority, then they win all of their matchups. And the reason for that is, if someone has a majority, meaning if they have over half of the first place votes, no matter how many votes anyone else has in all the other columns, it won't be more than what the person with the majority has, because the person with the majority already has over half. So if a candidate does have a majority, then they beat everyone else with over half of the votes. They have over half of the votes, so they're going to beat everyone else. Okay. So what this shows is if somebody has a majority, then they win all of their matchups. Okay. Okay, so what we have to do now is we have to figure out how many votes do we put in this fourth column to give EM a majority. So everyone else has Everyone else is 17 plus 18 plus 12, which is 47. So everyone else is 47 votes. So for EM to have a majority, EM has to have more than everyone else combined. So EM needs at least 48 votes in column 4 to have a majority. Okay, and if they have a majority, that means they win all of their matchups in pairwise comparison, so they win. So that's the answer to that first question. We would need to give EM at least 48 votes in that last column so that they win. And again, when you guys look at the slides, the following slide will have that stuff that we just wrote down worked out. Okay. So now I want to go back and answer the second question. The second question is, how many points will a majority candidate get if we use pairwise comparison and there's 4 candidates? Okay. So what we just said is a majority candidate wins all of their matchups. Okay, so let me just scroll down a little bit. Okay, so a majority candidate. That's bad. Okay, I'll write here. A majority candidate wins all of its matchups. Wins all of its matchups. So with 4 candidates, that means with 4 candidates, the majority candidate would be matched up with 3 other people. And if he's matched up with 3 other people and he won all of his matchups, that means he gets 3 points. So if there's 4 candidates, then they win all 3 matchups. So they get 3 points. If there were 5 candidates, then they would have 4 matchups. Each person has 4 matchups. So a majority candidate, because a majority candidate wins all of its matchups, they would win all 4 of their matchups. And in that case, they would get 4 points. Okay, so that's the answer to that second question. Okay. All right, so that's the answer to that second question. All right, and in the slides, it has the answer to that question worked out here. If you guys need to refer to it. All right, so I want to do another example. So this is another slickest Game of Thrones character example, and we've looked at this a couple times. But there's 17 students in the class that are voting on the slickest character in Game of Thrones, and there's 3 candidates: Varys, who's going to be V; Littlefinger, who's going to be L; and then Jaqen, who's going to be J. And then we have this preference schedule. So the first question that I want to ask is, who wins? Who wins if we use plurality? So using plurality, we got to count the first place votes. So this should be quick. But J has 6 from that first column. L has 5 in one column, and then 2 in another. So overall, that's 7. And then V has 4. So L wins using plurality. So L wins using plurality. So L wins using plurality. The next question is, how many points does that character receive if we use pairwise comparison? And then the third question is, which character would win if we use pairwise comparison? So to answer those two questions, we've got to look at each of the matchups. So for the matchups, we have J versus V. We'll have J versus L. And then we'll have V versus L. So those are the 3 matchups. So the matchup with the J and V. In the first column, J is higher, so J gets those 6 people. In the second column, V is higher, so V gets those 5. In the third column, V is higher, so V gets those 4. And the last column, J is higher, so J gets those 2. So J overall has 8, and then V overall has 9. So that means that V wins. So I'm just going to circle V. So V wins. Actually, let me use a different color. Oops. So V wins that matchup. Alright, so looking at J versus L, in the first column J is higher, so J gets those 6. In the second column L is higher, so L gets those 5. In the third column J is higher, so J gets those 4. And the last column L is higher, so L gets those 2. So overall L has 7, and J has, J has 10. So here, J wins. So J wins this matchup. Whoops. Alright. So J wins that matchup. And then there's one more matchup that we got to look at. So we still got to look at the matchup with V and L. So the matchup with V versus L. In that first column, V is higher, so V gets those 6. On the second column, L is higher, so L gets those 5. In the third column, V is higher, so V gets those 4. And then the last column, L is higher, so L gets those 2. So overall, L gets 7, and V gets 10. Okay. Alright, so looking at that now, V has more points, so V wins that matchup. V wins that matchup. I just want to make sure that that's okay, that I don't have a typo, that I didn't mess up there. J versus V, J gets 8, and V gets 9. Yeah, I think that looks good. Okay. Alright, so now we need to write down how many points each person has. So J won one matchup. So J has 1 point. So J has 1 point. V won both of his matchups. So V has 2 points. And then L won no matchup. So L has 0 points. Okay, so overall, V has the most, so V wins. So V wins using pairwise comparison. And in fact, V won both of his matchups because V beat L and V beat J. If somebody wins all their matchups, they're a Condorcet candidate. So V actually is a Condorcet candidate. So I'm going to put that in parentheses here. So V is a Condorcet candidate. Alright, so V is a Condorcet candidate. Okay, so we've answered the first three questions. The person who won using plurality is L. How many points did L get using pairwise comparison? L got 0. And then the person who won using pairwise comparison is V. And V was actually a Condorcet candidate. The last question is, what does this say about plurality and the Condorcet criterion? Well, using plurality, we just found an example where the plurality winner, which was L, lost. Sorry, that's not right. Let me fix that. So we just found an example. We're using plurality. The Condorcet candidate. The Condorcet candidate is V. Varus. The Condorcet candidate lost using plurality. So since the Condorcet candidate lost, that means that plurality violates the Condorcet criterion. So let me write that down. So since the Condorcet candidate lost, and the Condorcet candidate was V, so since the Condorcet candidate V lost, this shows that plurality violates the Condorcet criterion. Alright. Okay, so the following couple slides have that stuff that we just wrote down worked out. Alright. Yeah, so we just showed that the plurality violates the Condorcet criterion. Alright, so I want to do another example with the same preference schedule, but now look at it using plurality with elimination. So using plurality with elimination, I want to know who gets eliminated in the first round, and then who would end up winning. And then the third question is, I want to ask, does plurality with elimination satisfy the Condorcet criterion? Okay, so with plurality with elimination, I got to start off by writing down again how many first place votes each person has. So J, remember, has 6. So J has 6, L has 7, and V has 4. And then we got to see, does anyone have a majority? So the total number of votes is 6 plus 7 plus 4, which is 17. And then we got to figure out 17 divided by 2. And if we work out 17 divided by 2 with the calculator, that's 8.5. So a majority candidate would need over 8.5 votes. So no one has over 8.5 votes. So no one has a majority. So no one is a majority yet, so we eliminate the person who has the fewest. So that means we eliminate Varus. So V gets eliminated. Okay, so after we eliminate V, let's draw the new preference schedule. So we'll still have the same columns. We'll still have 6, and then 5, and then 4, and then 2. But now that V is eliminated, we'll just have a first place and a second place. So after V gets eliminated, the order of the first column is J still is in the top spot, but then since V is gone here, L gets bumped up and takes that spot. So if we continue to go like that in the second column, L is still in the top spot, and then V is gone, and then J takes V's spot. So J will end up in that second spot. In the next column, V, after V gets eliminated, we'll have J getting bumped up and then L sliding up as well. In the last column, V just gets eliminated from that bottom spot, and then we have L and J where they are. So again, now with this preference schedule, we got to count how many first place votes each person has. Okay, so I'm just going to switch to a different color. So if we count votes here, J now has 6 plus 4, which is 10. And then L has 5 plus 2, which is 7. So J at this point has over 8.5. Because J has 10. So this is a majority. So that means that J wins using plurality with elimination. So when we use plurality, I'm just going to abbreviate, plurality with elimination. So when we use plurality with elimination, J ended up winning. Okay. So the third question here was, does plurality with elimination satisfy the Condorcet criterion? Okay, so if we go back to our earlier example, V was the Condorcet candidate. That hasn't changed because the table hasn't changed. The V was the Condorcet candidate. When we use plurality with elimination, J wins. J wins when we use plurality with elimination. So that means the Condorcet candidate, V, lost. If we can find one example where the Condorcet candidate loses, that shows violation. So this shows plurality with elimination also violates the Condorcet criterion. Okay, so let me switch to another color. Whoops. So this shows that plurality with elimination violates the Condorcet criterion. So far, we've shown that plurality violates the Condorcet criterion, plurality with elimination violates the Condorcet criterion, and we showed that pairwise comparison, that was the very first one we looked at, satisfies the Condorcet criterion. Okay. So again, when you refer to the lecture slides, these following couple lecture slides have that work that we just did worked out. And again, what we concluded at the end of this example is that plurality with elimination violates the Condorcet criterion. Okay, so I want to do another example. So for this one, this example is going to involve the board account, and ultimately testing does the board account violate or satisfy the Condorcet criterion. So we've seen this example before with the Academy Awards, and we had these 4 movies that are vying for Best Picture. There's Arrival, which is A. So Arrival, which is A. There's Hidden Figures, which is H. La La Land, which is L. And then Moonlight, which is M. There's these 4 pictures, and we have this preference schedule that we've looked at before. The first question that I want to ask is, which movie wins if we use the board account? So that question I'm actually going to leave for you guys. But it turns out, so if we use the Borda method, it turns out that Arrival wins. But you guys should work that out for practice. So using the board account, Arrival wins. The next question that I want to ask is, which movie wins if we were to use pairwise comparison? So which movie wins if we were to use pairwise comparison? Okay. So I'm just peeking at my slides a little bit. That we've actually worked out before. When we did our lecture on pairwise comparison, we actually worked that out. So when we use pairwise comparison, actually for that, let me just refer to my slides. Let me just refer to my slides now. Okay. So what we just said before is that a rival wins using the board account. And when we talked about pairwise comparison, had that lecture on pairwise comparison, we got that Moonlight one using pairwise comparison. Let me write that up here. So when we use pairwise comparison, M won. So M, which was Moonlight, won. And in fact, when we did that, M actually won all of its matchups. M was a Condorcet candidate. M was a Condorcet candidate. So you guys should look back at your slides, at the earlier slides when we talked about pairwise comparison, to see that earlier matchup, but it turned out that M won all of its matchups. Whoops. M won all of its matchups, so M was a Condorcet candidate. Okay. So the final question here is, what does this say about the board account and the Condorcet criterion? Well, the Condorcet candidate is M. If we use the board account, the Condorcet candidate, Moonlight, M, loses. This shows that the board account also violates the Condorcet criterion. So since the Condorcet candidate loses using the board account, this shows that the board account violates the Condorcet criterion. This shows that the board account violates the Condorcet criterion. So violates, sorry, my handwriting is a little bad there. Sorry, the board account violates the Condorcet criterion. So again, remember that if we want to show that a voting method violates the Condorcet criterion, we just got to find one example where a Condorcet candidate, whoops, sorry, I just realized that I forgot to write candidate here. Let me just add that in. Since the Condorcet candidate loses. So remember, if we want to show that a voting method violates the Condorcet criterion, we just need to find one example where the Condorcet candidate loses. And here, we did that. This one example was an example where the Condorcet candidate, Moonlight, lost. Okay. If you want to show a voting method satisfies the Condorcet criterion, you have to argue that anytime there's a Condorcet candidate in any situation, that person has to win. Okay. Alright, so moving on. So the next couple of slides have that stuff that we just wrote down, worked down. Okay. Alright, so I want to point out one key thing. So we sort of mentioned this before, but it turns out that anytime a candidate gets over half of the first place votes, meaning that they're a majority candidate, so this means they are a majority candidate. This means they are a majority candidate. If they get over half of the first place votes, what that means is they had to beat every other candidate when you look at matchups, because they have over half of the vote. So there's no way anybody else could have more than them. So because of that, anytime there's a majority candidate, they win all their matchups. They win all of their head-to-head matchups. That means they're guaranteed to always be a Condorcet candidate. So a majority candidate is always a Condorcet candidate. I'm going to circle that. A majority candidate is always a Condorcet candidate, because a majority candidate will always win all of their matchups. because they beat everyone else with over half of the vote. Okay. Okay, so what that means is, if the voting system satisfies, if it satisfies the Condorcet criterion, then if there is a majority candidate, that person has to win. Because if there is a majority candidate, they have to be a Condorcet candidate, like this thing set up here. And if there's a Condorcet candidate, and the voting method satisfied the Condorcet criterion, that means that person had to win. Okay. So the key theorem here says that any voting method or voting system where the Condorcet criterion holds, or like is satisfied, the majority criterion is also satisfied. So the reason for that is, if you want to show the majority criterion is satisfied, you have to show that anytime there's a majority candidate, that person has to win. So the reason for that is, if someone is a majority candidate, they are also a Condorcet candidate, like we circled over here, because they had to have won all their matchups. They are also a Condorcet candidate. And we're assuming that the Condorcet criterion is satisfied. So if the Condorcet, I'm just going to abbreviate, if the Condorcet criterion is satisfied, that person must win. Because the Condorcet criterion, to satisfy it, anytime there's a Condorcet candidate, that person has to win. Okay. So just looking at what we've said over here, we've just said that if someone is a majority candidate, that person has to win. That shows this voting method satisfies the majority criterion. So this shows the voting method, whatever it is, the voting method satisfies, underline satisfies the majority criterion. Okay. The key thing, again, to take away from this is that the majority candidate is always a Condorcet candidate, because a majority candidate will definitely win all of its matchups, and it's going to beat all the other candidates because it gets over half of the vote. Okay, so I'm going to do one other example. So this one's going to be multiple choice, more in line with like the types of questions you guys might see in the worksheets. Okay, so the question is, which of the following is not true? So there's a bunch of possible answer choices. Which of the following is not true? Part A says, a majority candidate always wins all of their matchups. So if I look at A, so A says, a majority candidate always wins all of their matchups. This is what we just said on the previous slide. If I go back to the previous slide says that a majority candidate wins all of its matchups because it beats everyone else with over half of the vote. So A is true. A majority candidate beats all other candidates in its matchups with over half the vote. So that means the majority candidate wins all of its matchups. So this is true. So A is true. Okay, so that means, well, in this question, we were looking for which one is not true. So A was true, so it can't be A. And at this point, we know that it's not E. It can't be A and C. Okay, so now we gotta look at the other answer choices. Let's look at B. So B says, one example where a Condorcet candidate wins an election using an unknown voting method shows that the unknown voting method satisfies the Condorcet criterion. Let's look at again. If we have one example where a Condorcet candidate wins an election using an unknown voting method, that shows that the unknown voting method satisfies the Condorcet criterion. So remember, to satisfy the Condorcet criterion, you got to show that a Condorcet candidate will always win an election in all situations. So all B says is, all this says is that the Condorcet candidate wins in this one example, and I'm going to underline one example. But that's not enough for satisfies. That's not enough to show satisfies. This is not enough to show satisfies. In general, one example is not enough to show satisfies. Okay, so this is not enough to show satisfies. Okay. One sec. Okay, so this is not enough to show satisfies. So what that means is B is not true. I don't like that color there. Switch back to black. So this is not true. So B is not true. Okay, so then we gotta look at part C. So if the unknown voting method violates the Condorcet criterion, then it is possible for a Condorcet candidate to win. Okay. So let's look at C. So this is saying that the unknown voting method violates the Condorcet criterion. Okay, so let's break this down. So if the voting method violates the Condorcet criterion, if the voting method violates the Condorcet criterion, I'm just going to abbreviate. If it violates the Condorcet criterion, this means that there's some situation where a Condorcet candidate loses. This means there is some situation I'm going to erase that and write it better. There is some situation where the Condorcet candidate loses. So there's some situation where the Condorcet candidate loses. This does not mean a Condorcet candidate will always lose. So this does not mean a Condorcet candidate Condorcet candidate will always, I'm going to underline always, will always lose. Okay, so again, if the voting method violates the Condorcet criterion, that means that there's some situation where the Condorcet candidate loses. It does not have to happen all the time. So the Condorcet candidate will not always lose. There definitely could be situations where the Condorcet candidate wins. There may be situations where the Condorcet candidate wins. Okay, so now looking at the statement, what this was saying is, if the unknown voting method violates the Condorcet criterion, then it is possible for a Condorcet candidate to win. So this is true. It's definitely possible. All right, so now going back to the question was asking which of the following is not true. The one that's not true, so C was true. We don't want that. And that also eliminates D. The one that's not true, the only one that wasn't true is B. So B is the answer. Okay. So this is a really good example because it really breaks down a lot of what it means for a voting method to satisfy the Condorcet criterion and what it means to violate it. And there's a lot of subtlety there, which is why this section here where we're talking about fairness conditions is more challenging. Okay. So the following slides, if you look at the lecture slides, have each of those answer choices broken down. So B was the one that was not true. C was also true. So just to recap, so far we've looked at 3 fairness conditions. We've looked at the majority criterion, we looked at monotonicity, and today we looked at the Condorcet criterion. And with the Condorcet criterion, out of the 4 voting methods, the only one that satisfied it was pairwise comparison. If we look at this table so far, the only voting method that actually satisfies all 3 criteria, majority, monotonicity, and Condorcet, the only one so far that satisfies all of them is pairwise comparison.